I would like to start by thanking the organizers for giving us the opportunity of presenting our work in this conference. As we know, one of the main issues with quantum computers is the coherence. That is the fact that the stored quantum information is lost because of the interaction of the system with the environment. Several strategies have been proposed in order to deal with this issue. For instance, the use of error correction protocols that allow to detect and fix that errors that might occur over a short time scale. Another suggestion is trying to find self-correcting memories. That is, quantum systems on which we can store quantum information so that it is preserved for long enough time without the need of external intervention. And when I say for long enough time, it means that the time of coherence, or the memory time, should scale exponentially with the system size. Now, the typical family of systems to search for self-correcting memories is a family of topologically ordered systems. So these are quantum systems governed by local Hamiltonians whose ground spaces are degenerate and that satisfy some very nice properties at zero temperature. For instance, they are stable against weak local perturbations, and also if you take a couple of ground states, it is not possible to distinguish them if we use just local observables. So for the last 15 years, there have been a lot of work done in this line of research. Let me simply highlight that in 4 dimensions, it is known that there are self-correcting memories, and we have the prominent example of the 4D toric code. Of course, it would be interesting to have, for practical reasons, examples in 2D and 3D. And in 3D, there has been a lot of effort, which has led to the discovery of interesting systems such as the Haas cubic code. As for the 2-dimensional case, the general belief is that there are no self-correcting memories. And since this is the setting in which we are going to stay for the rest of the talk, we are going to review some of the results there. So one of the main notions in this setting is the so-called energy barrier. Imagine that we have 2 orthogonal ground states, and we have a sequence of local operators that allow to go from one ground state to the other. So when we apply these local operators, we move through a sequence of states, and this somehow mimics the thermalization process, this loss of information. Now, among this finite sequence, there will be a moment in which we reach a maximal gap with respect to the ground state energy. So the idea is that if we consider the infimum of this gap, energy gap, for all possible sequences of this type, this is what is called the energy barrier. And then Arrhenius' law tells us that for a quantum system, the memory lifetime should scale like the exponential of the energy barrier. So in other words, if we want to search for systems that are self-correcting memories, we should look for systems that have a microscopic energy barrier, an energy barrier that scales with the system size. This idea actually helps us to understand why in the classical case, the 1-dimensional IC model is not a self-correcting memory and the 2-dimensional IC model is, in the classical case. This idea is also behind some of the no-go results that have been established in the 2-dimensional case, although there are also some positive results, which roughly speaking say that even if these sequences of states that mimic thermalization process and with low energy barriers may exist, it may happen that they are not very typical in the landscape of all possible sequences. So in other words, from a ballistic point of view, it may happen that quantum information is still protected. And this phenomenon is what is called entropic protection. So in this talk, I would like to focus on a specific family of topologically ordered systems called quantum double models introduced by Kitaev. And in this setting, the first formal result was obtained by Aliki, Fanes, and Horodecki for the toric code in 2009. So they proved that the toric code is not a self-correcting memory. Several years later, using a different strategy, Komarland and Cardinal and Teme extended this negative result for all abelian quantum models. And what we do is to extend these results, using also a different strategy, to an arbitrary quantum double model. So in the rest of the talk, I'm going to explain some of the ideas behind the proof of our result and its relation with the ideas of the other previous results. First, let us start recalling the quantum double model. So we fix some finite squared lattice, and we assume that it has periodic boundary conditions. We have to give to every edge an orientation. So just for convenience, we are going to assume that the horizontal edges are orientated pointing left, and that the vertical edges are pointing down. We are also going to fix a finite group, which has associated group algebra, which is simply a finite dimensional Hilbert space with a fixed orthonormal basis that we identify with the elements of the group. Now, at every edge of the system, we are going to fix a local Hilbert space, which is yet the group algebra, and we will have an associate space of observables. And of course, for the global system, we will have an associate Hilbert space and space of observables, just tensorizing over all edges of the lattice. And the dynamics of the system is going to be governed by a local Hamiltonian, which is made of, essentially, it's made of two types of local terms. For every vertex, we have a vertex operator that just acts on the 4 edges incident to that vertex. And for every plaquette, we have a plaquette operator which only acts on the edges that form or surround that plaquette. And without giving an explicit formula, let me simply say that these local terms are pairwise commuting and projectors. So once we have our system, now let it interact with a thermal bath at inverse temperature beta. So we have to set some extra conditions to describe the dynamics, but the theory of open quantum systems tell us that the dynamics of, if we look for instance at the Heisenberg picture, is given or described in terms of a quantum Markov semigroup that has a generator called the Davis generator, which consists of 2 parts. So the first part could be the generator of the time evolution operator if S was a closed system. And then the second part is the so-called dissipative part, which contains the information of the interaction with respect to between the system and the thermal bath. And this quantum Markov semigroup has some very nice properties. For instance, if we look at the Schrödinger picture, one can check that if we apply to the Gibbs state of the system at temperature beta, the time evolution operator, the semigroup, this state is invariant. And that if we take an arbitrary state and we apply the time evolution operator, then we have that the state rho of t, the time t, is closer and closer to this Gibbs state and the time goes to infinity. This idea is actually behind of the proof of Komar, Landon Cardinal, and Teme that abelian quantum double models are not self-correcting memories. Essentially what they do is to show that the mixing time can be estimated from above by first a factor that increases polynomially with the system size, and a second factor which, roughly speaking, is the exponential of the energy barrier. They show that for this model, the energy barrier is uniformly bounded in terms of the system size, independent of the system size. And so they conclude that the mixing time can grow at most polynomially in n, the system size. This means that it is not a self-correcting memory, because remember that for a self-correcting memory, we want that the time scales exponentially with the system size. This is, however, not the point of view that we are going to follow. So let's go back to the Heisenberg picture and let us define the following weighted scalar product. So it can be shown that the dissipative term with respect to this product is positive semi-definite. And actually the only elements that are in the kernel of this operator are the multiples of the identity. But the main observation is that the lifetime of this quantum double model as a memory is directly related to the spectral gap or the dissipative part of the Davis generator. So if we are able to prove that the spectral gap of the dissipative term can be lower bounded by a constant independent of the system size, then this would mean that the system is not a self-correcting memory. Let's say memory lifetime would be short. This is actually what Aliki, Fanes, and Horodecki proved for the toric code, and this is also what we are going to prove for an arbitrary quantum double models. So what we prove is that the gap of the dissipative term is lower bounded by a constant of the following type. So here, the important thing is that lambda and c are constant that may depend on the temperature and also on the interaction between the system and the bath, but they are independent on the system size. Now, before explaining how this proof, in order to explain the proof of this theorem, let us explain a little bit more about how Aliki, Fanes, and Horodecki proved this result for the toric code. So the dissipative part of the Davis generator is actually made of some local terms that act on small regions around the edges. Now, if we identify the space of global observables with this Hilbert space, we can actually define a Hamiltonian in this Hilbert space, which is made of local terms. And these local terms are going to be defined from the local terms that form the dissipative part of the generators using the following formula. So without going into further details, let me simply point out that as a consequence of the properties of the Davis generator, this Hamiltonian is local, it is frustration-free, the purification of the Gibbs state is the unique ground state, and moreover, the gap of this new Hamiltonian is the same as the gap of the dissipative part of the Davis generator. So now the problem is reduced to estimating the gap of this new Hamiltonian. And what Aliki Fanes and Horodeki do is to work directly with this Hamiltonian and try to estimate it from below by heart. Now, we also are going to do that, but instead of working directly with this new Hamiltonian, we are going to apply techniques that come from the theory of tensor networks. And before going into more detail, let me simply sketch how the proof is going to develop. So first, we are going to consider the purification of the Gibbs state, and we are going to show that it has a very nice PEPS description. Now, from this PEPS description, we are going to define a parent Hamiltonian, and we are going to show that this state is the only ground state of the Hamiltonian. And second, that the gap of this parent Hamiltonian can be lower bounded by a constant that is independent of the system size. And then as a final step, we can compare the parent Hamiltonian and the Davis Hamiltonian, and although they may be different, we prove that the gap of this Davis Hamiltonian can be lower bounded by the gap of the parent Hamiltonian times some factor which is independent of the system size. So let's go step by step. So to find the PEPS representation of a purified Gibbs state, instead of working with the purification point of view, we are going to stick to the operator notation. So we are going to consider the Gibbs state as an operator, but forgetting about the partition function. And we are going to find a PEPO description of this operator. Now, remember that this Hamiltonian is made of local terms that are pairwise commuting. So we can factorize this Gibbs state in terms of exponential factors which act just locally. And moreover, since these local terms are projections, we can even find some simpler formulas for them in terms of the vertex operators and the Plaquette operators. So the strategy to find a PEPO description of the Gibbs state is the following. We are going to find a PEPO description of the vertex and Plaquette operators that form the Hamiltonian. Then from that, we are going to obtain PEPO description of these exponential factors. And then we are going to put everything together to get a PEPO description of the Gibbs state. So let us start with the vertex operator. And to give an explicit definition, the explicit formula for the vertex operator, we are going to define first two types of operators from the group algebra. So L, which is the left multiplication operator by G, and R, which is the right multiplication operator by the inverse of G. Now, the vertex operator is defined in the following way. So it is a sum of terms, and each term is a tensor product of operators, each operator acting on an edge. And for each edge, we choose L or R according to the orientation. So for instance, if the edge is orientated pointing at the vertex, then we will take the operator R. And if the orientation points away from the vertex, then we will take the operator G. It is very easy to see that this operator has the following easy PEPO description in terms of a tensor which only has two virtual indices. So here in the physical part, we have to put an operator T, which will be L or R according to the orientation of the edge we are looking at. From this PEPO description, from this tensor, we can immediately get the description of the exponential version. For that, we simply define a weight operator, which is simply an invertible operator acting on the group algebra. And it is very easy to see that if we take the above tensor and we contract on the virtual indices this weighted operator, then the resulting tensor is actually the one that gives you the PEPO descriptor of this exponential factor. Now, for the Plaquette operator, we do a similar argument. So the definition of the Plaquette operator is the following. So we have a sum of terms, and each term has an operator factor, which is simply a tensor product of projectors, each one acting on an edge. And then we have a scalar coefficient, which is given in terms of the regular character of the group. So remember that the regular character of the group is defined for an element G as the cardinality of the group is if this element G is the unit, and 0 otherwise. And in the Plaquette operator formula, we see that this regular character is evaluated on the product of G1, G2, and the inverse of G3 and G4, the product of these terms. And the fact that we choose G or its inverse in this product depends on the orientation of the associated edge. So G1 and G2 here, they correspond to edges that are orientated counterclockwise, while G3 and G4, they are associated to edges that are oriented clockwise. And well, to find a PEPO description, to find a PEPO description, we simply have to realize that the regular character can be actually written as the trace of the product of the left multiplication operators from a previous slide in the following way. So that we can again find a PEPO descriptor in terms of individual tensors that have only 2 virtual indices. And now in these 2 virtual indices, this left multiplication operator is going to leave. And I'm writing here sigma sub p of g. This means that, of course, according to the edge on which this individual tensor acts, we have to choose g or the inverse of g. And once we have this description, we argue, as in the case of the vertex operator, this exponential version of the Plaquette operator can be easily obtained by defining a proper weight operator acting on the virtual indices. So there is nothing more, and it's very easy to see that this resulting index, when we plug in these weights, then it gives you the PEPO descriptor of the Plaquette operator. So summarizing, if we now fix on one edge, we have 4 individual tensors acting on it. So 2 tensors that come from the adjacent Plaquettes, and other 2 tensors that come from the star operators. So of course we have to put them together, and then we will obtain the full edge tensor, which of course have 8 virtual indices. Now it is possible to give an explicit description of this tensor, but because of the weights, it's going to be rather long. However, if we forget for a moment about the weights, and we consider the tensor without the weights, then it is possible to give an easy description here. So you see that although this tensor have 8 virtual indices, we see that this tensor can be actually described just in terms of 3 elements of the group. This is a manifestation of the fact that these individual tensors are very far from being injective. Okay, so now that we have the PEPO description and the PEPS description, or the purification, if we use the purification map, we can describe how the parent Hamiltonian looks like. So first, for every rectangular region, we can of course associate a tensor simply by placing on every edge the individual tensor that we obtained in the previous section and contracting the virtual indices accordingly. So the resulting tensor is, of course, can be seen as a map that goes from the boundary indices, the virtual boundary indices, into the physical part. And now we consider let us consider by PR, the node by PR, the orthogonal projector onto the image of this map. And to define the parent Hamiltonian, we consider the family G of rectangles whose dimensions is contained between m and 8 times n. And I will tell more about this number n in a moment. So the parent Hamiltonian is going to be defined as the sum over all rectangles in this family of the identity minus the orthogonal projections that are defined above. So this definition guarantees that the purification of the Gibbs state is going to be a ground state of this Hamiltonian. But now, if we want to guarantee that this is the only ground state of this Hamiltonian, then we have to play with this number n. And we can actually give an explicit formula, choose a suitable n so that this holds. And this n has to be chosen depending on the temperature. It is, of course, independent of the system size, but it depends on the temperature. Without giving the explicit formula for it, let me simply say that it is a number that grows exponentially with beta. So this means that if the temperature of the bath is big, this means that beta is small, we can take a boundary Hamiltonian with local terms that have a small range. But if the temperature is very low, which means that beta is big, then the boundary Hamiltonian will have local terms whose range is also big. So now that we have the boundary Hamiltonian, the next question is whether it is what happened with the gap. And before studying the gap of the boundary Hamiltonian, we can already establish a relation between the gap of the Davis Hamiltonian and the boundary Hamiltonian. And as I said before, these Hamiltonians are different, but their gaps can be related and through the following formula. So we have that the gap of the Davis Hamiltonian is lower bounded by the gap of the boundary Hamiltonian times some constant which is independent of the system size. So here again, this constant kappa and c may depend on the group, may also depend on the interaction of the, between the thermal bath and the system, and also even of the temperature, but they are independent of the system size. And now the final step is to show that the gap of the boundary Hamiltonian, as we define it, is lower bounded by a constant that is independent of the system size. And for that, we are going to analyze the boundary states and to show that they satisfy a property which is called approximate factorization. So let us go back to the tensor description, so the tensor associated to a rectangular region R, that, as I said before, we can see as a map going from the boundary virtual indices into the physical indices. So the boundary state is defined as the following product. So we multiply the R from the left by its adjoint. So of course the boundary state is simply a map that goes from the boundary terms into the boundary. This is not the representation that I'm going to use in terms of bras and kets. What I'm going to do is the following. I'm going to take the bra picture and I'm going to put it below the ket picture. So in other words, what we are doing is so looking at this row as a map from virtual indices to virtual indices, I'm going to consider that I'm going to put the input indices in the lower part of the tensor and the output indices in the upper part of the tensor. And now with this representation of the boundary state, again, we have the weights acting on the boundary, but since these are invertible operators, to study the boundary state, we can forget about them. And if we remove these weights from the boundary, we can check that actually the terms that appear in the boundary have a very simple form. They can be described in the following form. So in the blue part is simply a tensor product of LG times LG, while in the red part is essentially like a right multiplication operator, depending just on some element of the group A. Okay, so the next thing that we do is that notice that the full contractions that appear on the plaquettes and on the vertices, they correspond to scalars factors. So we can take them out. And now we have a very long sum with many terms, each one having some weights. Now is where the technical part of the proof comes, because we have to show that in this big sum, we can work a little bit, we can rearrange terms so that a leading term with a very simple form appears. And this leading term is a tensor product of very simple elements. So it is going to be a tensor product of elements that live on the edges and on the boundaries. And these local terms are actually projectors. These are the projectors that you can see in the slide. And not only that, is that this leading term is really very, very close to the boundary state without weights, because this rest, we can estimate the operator norm of the rest of the terms, and it turns out that this decreases exponentially with the size of the rectangle, actually with respect to the area of the rectangle. So let me put all this informal information in a proper theorem. So what is the conclusion of this argument? First is that if we consider the orthogonal projector onto the support of the boundary state, then this can be described as a tensor product of local projectors. So it has a structure of as a tensor product. And the second important property is that the boundary state can be very well approximated by another state which has a tensor product structure that is compatible with the product structure of the orthogonal projector of the first point. Actually, not only that, but if we consider different rectangles, then these local terms sigma sub u, these building blocks that gives you the approximation of the boundary state, they are independent of the rectangle. And this homogeneity property is also very important. So putting all this information together, we are able to prove that the gap of the prime Hamiltonian is controlled from below by a constant that is independent of the system size and also of beta. And for that, we have to adapt some argument which was previously done for PEPS, which are injective, in another setting, to this setting. Because as I said before, here the tensors are very far from being injective. So we cannot apply directly those results. And well, this is essentially everything I wanted to talk about. So of course, a natural future line of research is trying to apply these techniques to study other systems, the process of thermalization of other systems. So we hope to get something in the future. And this is everything I wanted to say. So thank you very much.